Okay, we're segueing on into reactions, but before we get to the reactions that carboxylic acids undergo, let's just review real quickly how do you make a carboxylic acid. And here's two routes. One would be a primary alcohol. One would be to react to primary alcohol. Those of you who were in lab today, chromic acid, there's chromic acid right there, oxidizing agent. So you can oxidize a primary alcohol to a carboxylic acid. Why primary? Well, that's where your OH is. It's on the N carbon, and that's where your carboxylate or carboxyl group is going to end up on the N carbon. So you can't get here from a secondary alcohol. You can't start with your oxygen here and get a carboxyl group. All you can get is an ester, or ketone. So primary alcohol, carboxylic acid. Here's the other one, an aldehyde. An aldehyde, again, you got a carbon-oxygen double bond on the end, and you're going to a carboxylic acid. This is just showing the scheme. If you started with an alcohol, it will probably oxidize all the way to here. It's kind of going through an aldehyde and then forming that. And there's that scheme that I've been showing you right along. Alkane, alcohol, aldehyde, carboxylic acid, that's all oxidation. You're either losing hydrogens or you're gaining oxygen. So one oxygen going to two, that's oxidation. All this is showing you is that, you could take these molecules and burn them and form CO2, but you can't. Once you get to here, you can't come back here. It's very difficult to convert carbon dioxide back into an organic molecule. But we have this scheme because you can go down here to this point. You can come back by the reduction of these molecules and work your way back to an alkane. All right, now if we talk about carboxylic acids, how do they behave? Well, first of all, simply, if you put them in water, they hydrolyze. They dissociate. I probably want to say it that way. So if we take our acetic acid and we put it in water, it's going to form this ion and the hydronium ion. We're just showing it there as an H+, but in the presence of water, that H+ is an H3O+. It's an H+ plus a water molecule is an H3O+. That's the way it's floating around in the water. I'm putting it here as an equilibrium. This is acetic acid. This is the acid that's in vinegar. Equilibrium. At equilibrium, about 99% of the acetic acid is in the molecular form, and only 1% of it has actually dissociated. This is why we're calling these weak acids. They only partially dissociate. In contrast to something like HCl, which is a strong acid, and it dissociates 100%. All right, you've seen this in 1305. That if you put this in water, you just draw an arrow in one direction. It's going to completely dissociate. Because it completely dissociates, it makes the water a lot more acidic. Every hydrogen of the HCl is floating around in the water as a hydronium ion. Here, only 1% of them are. All right? But, and I have mentioned this before, you put ethanol in water and you get ethanol in water. Nothing happens to that H. All right, that's not an acidic on an alcohol. An OH on an alcohol is not acidic. It won't dissociate. It's not going to dissociate in water. It's going to dissolve in the water, and you think, well, something happened there. Yeah, but it just dissolved. It just hydrogen bonded with the water around it, but it did not form ions. So alcohols are not acidic. Carboxylic acids are acidic. Acetic acid, citric acid, dipic acid, all these carboxylic acids have an acidic proton because of this functional group right here. So that's dissociation. There's no chemical reaction here. It's just breaking apart in the water to form these ions. You evaporate off the water, you get your vinegar back. All right, so the first reaction here, the first real chemical reaction to talk about is just what you are also familiar with from 1305, is that an acid plus a base forms a salt and water. And what are carboxylic acids? They're acids. So if we were to take vinegar and react it with sodium hydroxide, we would get a salt and water. This is a neutralization reaction. We're starting out with an acid and a base. This is acidic, pH less than 7. This is basic, pH greater than 7. We're going to end up with a salt water, which could have a pH right around 7. We have neutralized, the acid and the base have neutralized one another. So let's take, I'm going to pick on acetic acid a lot. Here, let's keep it simple. Sodium hydroxide. That's a salt. That's ions and water. Here's your hydrogen and your OH forming your water. So this is, well, I said acetic acid, but the IUPAC name is ethanoic acid plus sodium hydroxide. What we're going to get here is sodium. Now we don't have ethanoic acid on the other side here. We've lost the hydrogen. We're going to take off the IC and add ATE. So this is actually called sodium ethanoate. That's the salt. That's the name of that salt. Sodium ethanoate. Its common name is acetic acid. We'll do the same thing with the common name. We'll drop the IC and add ATE. So those are the two names. Those are the two names of that salt, sodium ethanoate or sodium acetate. Sodium acetate is the common name. I mean, it's the most common name you'll see that called. If you went to look it up in a chemical catalog and you look for sodium ethanoate, I don't know if you'd find it, but you would find sodium acetate. You could buy that. All right, so that's neutralization. That's the acid-base reaction that carboxylic acids can undergo. This could be sodium hydroxide. It could be potassium hydroxide. Doesn't have to be sodium hydroxide. Just has to be a base. All right, so here it is talking about the naming of it. First add the cation's name, sodium. So you have sodium acetate, benzoic acid. You would react it with sodium hydroxide, you get sodium benzoate. Sodium benzoate is a preservative, saying it's found in cranberries, prunes, ketchup. It used to be in Coke, but they've taken it out of the Coke formula. They used to have it in there as a preservative, but there were some concerns about whether sodium benzoate could degrade into some other things. Here's another metal salt of a carboxylic acid, undeclinate. It's got a double bond here, 8 carbons, 9, 10, 11 carbons, and zinc, and it's in an athlete's foot. Cream or treatment is this zinc 10 undeclinate. I guess the 10, 1, 9, 10. So they're talking about where this carbon double bond begins. So zinc 10 undeclinate. Sodium citrate and citric acid together in a, let's say, a food. If you see that on a food label, that's buffering that food, and you might see that with soup, canned goods, canned soups. You might see some other acid here, but if you see contains citrate or sodium citrate, or it's sodium citrate, citric acid is keeping it at a certain pH so that food doesn't go bad and maintains a certain pH. Maintain its flavor, etc. Okay, here's the first one. Why don't you go ahead? We've talked about now the oxidation of a primary alcohol, an aldehyde, to form a carboxylic acid. So draw the carboxylic acid products here, and then finish out that reaction, the carboxylic acid reacting with KOH. Anyone else need to turn in their homework? Cool. Is Elaine here? Elaine Eubanks? Jose? Samantha? Jasmine? Okay, you get the carboxylic acid. Try to name these as well. Name these products. Yeah, we're going to talk a lot about naming today. The naming of these and esters can be a little challenging. You need to practice it. Are you waiting?
I'm trying to read it better up there.
What?
I'm trying to read it better up there.
Okay. If you have a pencil, then you can change it if you need be. Okay, the first one's a 4-carbon primary alcohol. So we're going to get what? A 4-carbon carboxylic acid, right? And what would we call that? 4-carbon carboxylic acid. It's not an aldehyde. Yeah, it's not an aldehyde. Butanoic acid. Yeah, Steen, it would have first formed butanal and then butanoic acid. So it could form the aldehyde, but in this case we're carrying it all the way to the carboxylic acid. Now the one below, we have pentanal. It's a 5-carbon aldehyde. So just to make the point that you can start either with a primary alcohol or an aldehyde and produce a carboxylic acid. 5 carbons. Right where you originally had an oxygen, you're now going to have 2 oxygens. You're going to have the carboxyl group. And what's that name? Pentanoic acid. And down here we have propanoic acid. We're reacting with KOH. All right, the H on the COOH is going to combine with the hydroxyl to make water. And the potassium ion is going to end up right here. And what's the name of that? Okay, potassium, I guess that has 2 S's in it, right? Potassium. So the propanoic goes to propanoate. And the acid gets dropped. It's potassium propanoate. That's a salt. Potassium propanoate. All right, so there's some simple reactions. Let's see, are we ready to go into the, can I move on? Got those? This is just for your information. Here's lactic acid, it's carboxylic acid. You can produce this in the course of metabolizing, typically anaerobically, so it's really heavy exercise where you're really burning fuel faster than you can get oxygen. Your body will start anaerobic metabolism, produce lactic acid. Bacteria produce lactic acid from lots of different organic sources. But here you can make polylactic acid. Why would you want to do that? Well, it's a biodegradable plastic. Because it is a polymer that is being made from a naturally occurring metabolizable compound. You throw that in a landfill, and in time, the bacteria will chew it up and eat it back up again. So this is a way of, I mean, if we could make all of our plastic bags out of PLA, we would have less plastic floating around and for centuries before it degrades. Polylactic acid. About 4 or 5 years ago, Lay's potato chips on Earth Day launched Sun Chips in polylactic acid bags, PLA bags. They had to stop doing that because they couldn't get enough of that plastic to bag all their chips. So I don't know if they have gotten back to it. I don't know if the supplies have changed, but they were really trying to do something, environmentally conscious, which was kind of neat, but they were having trouble with their suppliers. They didn't make polylactic acid, but they were telling suppliers, you make it, we'll bag our chips in it. And the supply didn't keep up with the demand. That's polylactic acid. Okay, now, esters. Now I told you chapter 14 is going to kind of be carboxylic acids, what are they, how do we name them, et cetera, et cetera, et cetera. And then we're going to get into esters because you make esters from carboxylic acids. And what we're looking at here is this is an ester. All right, we're replacing that hydrogen there that was with the carboxylic acid. We've got another organic portion of the molecule developing here. So here's your ester linkage, a carbonyl and an ether. Carbonyl and an ether is an ester. The ether is right on, they're both on the same carbon. They're both emanating from the same carbon. This is an ester. You're familiar with esters. Matter of fact, you like esters. Let me convince you. They're mildly polar, and they're not as polar as a carboxylic acid because, just to repeat it again, you don't have a hydrogen on either one of these oxygens. There's no hydrogen. And it's the OH bond that is the most polar. So we got an OC, which isn't as polar as an OH. So these, you still have electronegative oxygens here. You still have some polarity at that portion of the molecule, but it's not as polar as carboxylic acids. All right, here's where you like them. Lots of fruits. They're naturally occurring. They're very fragrant. Sometimes they're put in as flavorants. They're certainly put in as attractive aromas. If I blindfolded you and walked you through HEB and you were able to figure out where the strawberries are, you would be figuring that out because you'd be smelling the ester that's coming off the strawberries. Or bananas. Say, oh, I smell bananas. Isoamyl acetate. Pineapples. All right, so each of these fruits a different ester. Isobutyl methanoate, 3-methylbutyl ethanoate, octoethanoate, methylbutanoate, methylbutanoate. We'll get into how to name these. But there's the ester coming off of apples, off of peaches, or apricots here. Pentylbutanoate. Pentyl, 1, 2, 3, 4, 5 carbons. So we've got 5 carbons. And butanoate, 1, 2, 3, 4 carbons here with this carboxyl or carboxylate group. All right, and there's a IUPAC name and a common name for many of these. This one is unique. The mushroom, or not the mushrooms, the strawberries. The strawberries, you replace the oxygen right here with the sulfur, you won't see very many of these. This is just an example. This is a thioester, where instead of a OH there, that we would have had an SH, and now we've put something on there, and that's a thioester. All right, so that's kind of interesting, unique molecule there. Okay, this is going to be a really key reaction, esterification. How do you make an ester? This is what we're talking about here. And the general reaction is a carboxylic acid plus an alcohol forms an ester plus water. Let me see if the next slide says that. Yeah, okay, the next slide says it. This process is called esterification. The resulting functional group is an ester. It's a dehydration reaction. You'll see that a little better right here. So here's a good general statement of the esterification reaction right here. A carboxylic acid plus an alcohol yields an ester plus water. And you could see from all of those fruits and the esters that were associated with those fruits that you could take a carboxylic acid and react it with 10 different alcohols and you get 10 different esters. You could take an alcohol and react it with 10 different carboxylic acids and get 10 different esters. So there's just a lot of flexibility here. Just change the carboxylic acid, change the alcohol, and you're getting different esters. This one down here, I would like you to keep track of the fact that we've also produced a molecule of water. That's what we mean by the dehydration. But how are we dehydrating? We're dehydrating between these two molecules. We're getting a hydrogen and an oxygen, a hydrogen and a hydroxyl is producing a water molecule. So what are the names of the reactants and the products? Okay, let's name these reactants. What's our carboxylic acid called? Propanoic acid. And what's our alcohol? Methanol. I'm going to just say we've got a common name for it too, methyl alcohol, which will be a little bit helpful. And rather than just put this name together for you, and I'll give you some to put together on your own here, but this portion we're going to call methyl, and this portion we're going to call propanoate. It's 3 carbons long. All right, and I called it methyl propanoate. I did not call it propylmethanoate. Think, well, boy, is that different? Yeah, it's different. Methyl propanoate. This name is coming from what you want to key in on is the part of the molecule that's a carbon-oxygen double bond. That part of the molecule, you see it has some carbons attached to it. That part of the molecule is derived from a carboxylic acid. So ask yourself, what would I call that? If that were a carboxylic acid, I would call it propanoic acid. It doesn't have the hydrogen, so it's propanoate. What does it have? It has a methyl there. Methyl propanoate. All right, we'll do 5 or 6 of these so that you can start feeling comfortable with how to name esters. There's just aspirin is an ester. Let's see, where do we have the ester? Right here. We've got an ester right here. We've reacted this salicylic acid with the acetic anhydride, and we've formed this ester right here. We've got acetyl salicylic acid. So aspirin is an ester. Polyesters. Polyesters. How are they making these? Now they're making a polymer. Now let's just see what we've got here. We've got terphthalic acid. This is what we've got. It's kind of a lopsided 6-membered ring. That's what we're trying to show right there. We've got benzoic acid with another carboxyl group on the other end of it, para. Para to the first one. Now we're going to react this with a molecule that has an OH on both ends of it. So the very first reaction occurs to form an ester there. And then on the other side of it, you get another terphthalic acid, and the other side of this molecule reacts with it. Went too far there. You get water, and so then on the other side of this terphthalic acid, you get another ethanediol, and it just propagates down there. So it's repeating. This unit right here is your repeating unit. And what do you have over there? You've got another one of these over there, and then ethanediol here, another terphthalic acid, another ethanediol. You see? So you're forming that polymer. It's getting higher and higher molecular weight. I really don't know how many repeating units there are in polyesters, but this is polyester. All of you that have a water bottle, I see a bunch of them, and I have one. All right, all of you that have a water bottle, maybe even some of those of you that don't, you have some other bottle, that's what you have. It's made out of PETE, polyethylene terphthalate. We saw that in, where did we see that? Oh, in chapter 11, when we were looking at polymerization of alkenes. You can form these plastics. But here's another polymer, polyethylene terphthalate. Now this isn't biodegradable. You throw these in the landfill and they stay there. I don't know how long. I can't believe they stay there forever. Probably if they sit out in the sun, they will degrade. UV light will degrade them slowly, very, very slowly. But down in the ground, probably stay there a long time. So you make polyester fibers for fabric. Mylar, I don't know. What is, Kevlar is the bulletproof fiber, right? Kevlar?
Mylar is balloons.
Mylar, balloons.
And the little emergency blankets you get.
Okay, Mylar. Yeah. That's just showing it a little bit more. Okay, let's see here. Naming. So there we have there we have a 2-carbon carboxylic acid reacting with a 1-carbon alcohol, methyl alcohol. And what are we getting? We're getting methyl ethanoate. All right, so this is the IUPAC name, ethanoic acid. Its common name is acetic acid. So if we look at it from a common name point of view, acetic acid reacts with methyl alcohol to form methyl acetate. Methyl acetate. Okay, now, am I going too fast? I don't think I am, but am I? I'm going to put, right underneath here, I'm going to put like almost the opposite of this reaction, and we're going to finish it and name it. And then I want you to be able to compare the two names and start getting comfortable with how to name esters. So let's take a 1-carbon carboxylic acid and let's react it with a 2-carbon alcohol. So I'm just putting the shoes on the opposite foot. We're starting with a 1-carbon carboxylic acid reacting with a 2-carbon alcohol, and we're going to do this acid. It's a esterification reaction, and we're going to get. So what are we going to get? We're going to get. If we got a 1-carbon carboxylic acid here, this is the H that we're going to lose in the dehydration between these two molecules. So this is what that is going to look like. This is going to look like that in ester. We're going to lose this OH right here. So we're losing that OH, so this portion of the molecule is going to look like this. So there's our ester. Now, I just want you to kind of keep track of the difference over here. We ended up with 1 carbon here. Why? Because we had a 1-carbon alcohol. We ended up with 2 carbons here. Why? Because we started out with a 2-carbon carboxylic acid. Now the shoe's on the other foot. Just the opposite. We've got 1 carbon here. We've got 2 carbons here. So what do we call that?
Ethyl methanoate.
Yes. All right? And maybe the best way is to say what's it coming from? Methanoic acid and ethyl. Sometimes this doesn't write. Ethyl alcohol. And what do you have? Ethyl methanoate. Yes?
That's formic acid, right?
Yes. Yes. Common name. Remember, a 1-carbon species, you are familiar with formaldehyde. It's a 1-carbon aldehyde. This is formic acid. All right, we've got our common name up here. We've got methyl acetate. So what would be our common name down here? Someone else, like Jacob. Like Keeley.
What was the question?
What would we call this now? What would be the name of this molecule? Here's the IUPAC name of it here. So what is the common name of this NIC. Drop it and add. What do we add to it? Form, formate. We're starting with formic, so it's going to be ethyl formate. We do nothing with the alcohol. We just leave its name the same. Ethyl. Ethyl. It's an ethyl group. But in the common naming nomenclature, that's formic acid. So in the ester, it's going to convert to ethyl formate. Okay? Okay, so just compare this name with that name. Methyl ethanoate, here we have ethyl methanoate. Okay, so you have to look at the two parts of your ester and scope it out well. I've got a 1 carbon that is holding the carbon-oxygen double bond. That's my methanoate. I have 2 carbons over here as an alkyl group. There's no carbon-oxygen double bond on this. It's simply an ethyl group. I mean, that's just like an ethyl substituent on methanoate. It's just an ethyl substituent. Up here, we got a methyl substituent on a ethanoate. Okay, let me give you a really tough one. Here's a really tough one. And Steen isn't going to help you out on this one. Someone's got to come up with the name of this one. Here's an ester. This isn't a really tough one. This is a great one for a test. Okay, name that ester. Okay, you got 2 parts here. If I broke it right there, if I broke it into 2 parts, part on the right would have come from an alcohol. This part would have come on it from an alcohol. This part would have come from a carboxylic acid. Someone want to take a stab at it? We even let you go home tonight, right or wrong. All right? Yeah. There's no punitive. What? Who? What'd you say? What was the first part? Well, you're close. You're close. No, these aren't methyl groups. This is a propyl. What propyl is that? Isopropyl. That is isopropyl. And then what did you say? Benzoate. Okay, that's a really good one. I'm not sure if this one's on your homework or not, but it's probably something close. So it would be kind of nice to, you could do something like this. You could say, okay, I'm going to complete this reaction. I'm just repeating that molecule right there, plus water. No, is that plus water? Yeah, yeah. So it's would be this plus this yields that. And the name is already kind of steering us in the right direction. That we're naming this isopropyl benzoate. So what do these two reactants have to be to make that ester? Okay, isopropyl alcohol. And benzoic acid. Okay, you should, don't forget about this isopropyl group. Propyl, I mean, if we were looking at just propyl benzoate, it would be this. We would just have 3 carbons in a row. That's propyl benzoate. That's propyl benzoate. This is isopropyl benzoate. Good. Okay? You with me? This is just showing a little bit more about the naming. Look at this name. Let's go backwards from this name back up to that molecule. We've got ethyl butanoate. I see that name right there, butanoate. It's telling me that the 4-carbon portion of this ester has the carbon-oxygen double bond on it and the carbon oxygen. That's your butanoate. It's coming from butanoic acid. And then the simple substituent here is just ethyl, 2-carbon ethyl. Okay, so we have an ethyl there. Here we have an ethanoate. Why? Well, the 2-carbon portion is bearing the carbon-oxygen double bond. It would have started out as ethanoic acid. Yeah, there's your propyl. There's your simple propyl. 3 carbons in a row, not the isopropyl. Naming esters. Yeah, this is just showing it again. Oh, one thing I want to make sure you don't get confused about. Let's go back here. Let's go back here. Don't get confused. There's propyl ethanoate, but even if I drew it this way, you can see I've always been saying, okay, we've got the ethyl. So take the second part of the molecule, or well, where are we? We're here. Take the second part of the molecule, that's what comes first. Ethanoate is what comes second. That is that. Those are two the identical molecules. What have we done? Well, we have just started drawing this first and followed up with that. It doesn't matter whether it's drawn with the carboxylic acid first and the alcohol second, or the alcohol first, carboxylic acid second. We're going to put this first, propyl ethanoate. Okay, we're always putting the alkyl group name first and the portion that has the carbon-oxygen double bond, which would have come from a carboxylic acid, second. So whether it's drawn this way or that way, it's propyl ethanoate, okay? That's just, I don't want you to get confused by like that. You can see that I'm drawing it with the carboxylic acid leading in most cases, but there's no rule that says you have to draw it that way. And those are superimposable molecules. They have the same name. Okay, reactions of esters. Esterification is how do you make an ester. Now we want to look at, and there's two primary reactions. This is the first one, hydrolysis. So you take an ester, react it with water, and you break it back down into a carboxylic acid and an alcohol. Essentially what this is esterification in reverse. This is the reverse of esterification. We're taking an ester, react plus water, forms a carboxylic acid and an alcohol. We said that esterification is a carboxylic acid plus an alcohol forms an ester plus water. So you can see that is the reverse of that reaction. But if you took bananas and extracted all the esters out of it and then reacted it with water, if you were starting with an ester, you reacted it with water, what would you get? A carboxylic acid and an alcohol. This is a hydration reaction or hydrolysis. Hydrolysis. When we hydrated a double bond, we added hydration, we added the water to one molecule. We added it to one molecule. In hydrolysis, what are we doing? We're inserting this water in between here, and we're going to break it apart into an alcohol. And so that's why this kind of is referred to as hydrolysis. We're hydrolyzing these molecule into two molecules. Acid hydrolysis. Here's here's a 3-carbon carboxylic acid, a 3-carbon alcohol portion here. Here's your ester. Reacting with water in the presence of an acid. Yeah, and this is color coded, so you can see you got 2 hydrogens and an oxygen, 1 hydrogen, 2 hydrogens, and an oxygen. There's where your water came from. Or there's where your water went.
Can you go back to the previous slide? So, is all hydrolysis acid hydrolysis?
Yes, we're going to see another reaction, saponification, and we're going to react it with a base. Yeah, but it's not going to be hydrolysis. We're not reacting it with water. We're reacting it with a base. All right, so we're breaking it right here, inserting a hydrogen on there and an OH on this carbon, and we get propanoic acid and 1 propanol. Let's see, there another reaction to give here? Acid hydrolysis. Let me give you an ester here, and you complete the acid hydrolysis of it. All right, complete that reaction. That's the acid hydrolysis of this ester. We're starting out with an ester, and we're going to hydrolyze it. Okay. Sorry, I left you there for a little bit. Okay, we're gonna insert the water in here. We're gonna get, what do we got? 4 carbons there. We're gonna get an OH off of the water there, or a hydrogen off of the water there, and an OH off of the water there. All right, is that what most of you got? And what do we have over here? We have ethyl butanoate, and we're producing butanoic acid and ethanol. That's what we're getting out of it. butanoic acid, and ethanol. So that's the hydrolysis of an ester, of any ester. The pattern it follows. All right? I don't want to jump on into saponification. I'll do that on Wednesday. If there are some questions about your mold day or your mold day presentation or class presentation, the class project, or if there's some questions you have for your team members or information, why don't you take 5 minutes to go over that. If anyone has any particular questions for me, I'll take those as well. Your Chapter 14 homework will be due next Monday, so a week from today. And we'll finish Chapter 14, and I don't know if we'll get started on Chapter 15 actually on Wednesday.